Well, first of all, I would like to thank you for the invitation. It's a real pleasure to be here, and I hope that you find interesting what I'm going to tell you about. And this talk is, well, maybe a little bit different from what I usually do, because I wanted to give you a perspective on how I did get into quantum computing, because as Kevin mentioned, my background is not in physics. It seems that most people working today in quantum computing have a physics background, but my background is in computer science and mathematics. And in fact, I used to work in computability theory. My PhD, my dissertation was in Turing machines and that kind of thing. Then I worked for some time in applied machine learning. And a few years ago, I was working in this problem of classifying semifields. And semifields are a not very well known mathematical object. Most people know about fields. You know, you have a field with this addition and this multiplication, for instance, real numbers or complex numbers. And the semifield is a generalization of a field. And to us mathematicians, it's always interesting to study new ways of doing the same old things with a different light. Okay, so what we do with semifields is to remove some of the properties that a field has. So you know that, for instance, multiplication in a field, it's always commutative, associative. In semifields, it's not the case. Okay, so we keep this idea of having addition with the usual properties, but then multiplication has inverse for all the elements except the zero of the addition, but it is not in general associative. And removing this property makes this structure very, very complicated, because when you have the associative property, everything is more or less simple, and you have good theory, good theorems that classify and characterize what things are fields, even in the finite case. But when you remove this, we don't have a complete theory. In fact, this is something that has been studied by some very clever people, like, for instance, Donald Knuth, the famous author of The Art of Computer Programming and the author of TEG, the typesetting software. And in his PhD thesis, he used some computational power in order to classify the semifields in the finite case. But this was kind of difficult because of the limitations of both the algorithms and the hardware at the time. So, well, these people were able to classify some of the smallest, simplest objects of this type. But then there was this gap for almost 40 years in which no advance was made. Okay, so I got interested in this problem because a very good friend of mine, a colleague here at the Department of Mathematics in the University of Oviedo, used to work in this, and he asked me whether we could try and develop new algorithms to classify these structures. And we did. And in 2009, we made kind of a breakthrough because we were able to classify a new set of semifields for the first time in 40 years. And we discovered that there were a lot of new structures that were not covered by the theoretical constructions. And to do this, and this is where the connection to quantum computing starts to take shape, we used high performance computing. We parallelized a lot of our processes, but we needed 1 month of computation in 12 processors. So we had 12 processors running for 1 month in order to complete this classification. And then we improved our algorithms a little bit more, and we tackled the classification of even bigger sizes of semifields. Okay, so, well, we classify, for instance, commutative semifields of order 128, and, well, some other some other semifields of odd characteristic, but this was like getting more and more complicated. For instance, this last case that we classified, the semifields of order 7 to the 4th power, took more than 2 million computer hours. Okay, so this was crazy. It was like, well, this is not something that we can keep doing because it makes no sense. And then we kind of joking thought, well, maybe when we have quantum computers, we can try and do this classification for higher orders. Okay, this was back in, I don't know, maybe 2012 or 2011 or something like that. And then a few years later, we realized that, well, quantum computers were starting to be something that were not just prototypes anymore, but you could use these IBM quantum computers on the cloud and all that. So in 2017, we started learning about quantum computing with the goal of applying quantum techniques to this problem of classifying semifields. And we got hooked. We got hooked because, well, to me, this field is where everything that I like about science comes together, like physics and mathematics and computer science, and you can try and put everything together to get some advantage in your computations. So we were very excited to try and see what we could do with quantum algorithms, but we didn't know anything about quantum computing. So we tried to learn the techniques and try to get some results on this classification at the same time. So we started simple. We started with not the whole problem of classifying these semifields, because we knew that the quantum hardware was not there yet, and it's not there yet even five years later. So we tried and apply something that was a little bit simpler, which was the classification of those semifields that we had already obtained with classical methods into commutative and non-commutative semifields. This is one of the steps in the whole classification of these objects. It's not, of course, all that we need to do, but this is something that is important to know whether the semifield is commutative or not. And we realized that, well, this was a problem that it was kind of suitable for the kind of algorithms that quantum computers can speed up over classical methods. So we rewrote the problem of checking whether a semifield was commutative or not as a search problem. And then you know that for search problems, you have many different quantum algorithms. You have, for instance, Grover's algorithm, you have quantum walks, you can even do this with quantum adiabatic computing. And we started trying to obtain this quadratic speed up that these algorithms offer for our particular problem. And then at the same time that we were learning these techniques, we were obtaining results for our problem, and we published several papers about this this idea of using quantum techniques for this part of the semifields classification. But in this process, what we discover or what we realize is that although in the literature, these algorithms are kind of different, you learn about Grover's search and amplitude amplification, and it's kind of related to quantum walks, but it's not all unified under the same formalism, and it has not much to do with quantum adiabatic search algorithms. But we started to realize that there were some connections between these algorithms, and we came up with a generalization that we call quantum abstract detecting systems, in which we are not really interested in searching for a particular element, but on detecting whether that element exists or not. And with this small change, we were able to encompass every algorithm that we were using under this same formalism of quantum abstract detecting systems. And we came up with this definition, which is kind of abstract, but at the same time, kind of natural for search or for detection algorithms, quantum detection algorithms. That is why we call these quantum abstract detecting systems. And the idea is that you have some initial state and you have a unitary operator that you create from the definition of your problem, from some oracle or some function that you want to check whether it is satisfiable or not. And the idea is that when you do one of these constructions with these quantum abstract detecting systems, you get a new unitary operator that fixes the initial state if and only if, or well, yeah, if your problem has no is not satisfiable, then the unitary operator fixes your initial state. So this was the definition that was like behind all these different techniques that we were using to solve the problem of checking whether a semifield was commutative or not. And for instance, in the case of Grover's algorithm, this is exactly what we have. We have this oracle. So the whole unitary operator of the quantum abstract detecting system would be both the oracle plus Grover's diffusion operator. And this fixes or does not move the initial state if the oracle is trivial, if it does not mark any element. Okay, and this is something that you can also check that works for quantum walks and for different flavors of other algorithms, for instance, even for Deutsch-Jot's algorithm. And we were able to like put everything together. And well, as mathematicians, we always feel some pleasure when we are able to generalize some objects that were kind of related, but not unified, and put them all together under the same umbrella, so to say, okay? Another advantage of doing this is that we were able to define like global ways of doing detection, because you can start with this initial state and try to apply your unitary operator several times. And this is similar to maybe you know this Elliott-Boltzmann detection scheme, in which you move or not move the original state, the initial state, and then you measure and check whether something has happened in between. So we define this general way of doing detection with these quantum abstract detecting systems, and we were able to define and study properties like whether the procedure is efficient, whether the procedure is efficiently constructible, whether the procedure has what we call delta detecting time, several different properties that unify much of the theory that is behind all these quantum walks, Grover's algorithm, and all. Okay, and we published this in a paper in both in quantum information processing. The first one, it's called Quantum Abstract Detecting Systems. And then with one of our PhD students, we were able also to define a particular case that we call combinatorial and rotational quantum abstract detecting systems that have some special properties. And for instance, Grover's algorithm is one of these quantum abstract detecting systems. So by this time, we were already quite familiar with quantum techniques. And in my particular case, I was already in love with quantum computing. It was, as I mentioned before, a field that unified everything that I had been working on. And it was like new and well, a pleasure to discover so many great ideas and to be able to participate in kind of a revolution happening at the moment. Okay, so by that time, we were attending different conferences and trying to connect, network with different people. And in one conference, I met researchers from CERN that were also trying to apply quantum computing to different problems. In their case, of course, to problems related to high energy physics, but they were applying quantum machine learning techniques. And to me, machine learning has always been something that has attracted my interest a lot. I used to work in text classification with different techniques. So it was like, oh, okay, so I can also unify machine learning with quantum computing, and everything that I have been doing comes together again. So I started working with researchers from CERN, trying to see what these new ideas of quantum machine learning can offer for high energy physics. And we started collaborating about 2 years ago. And in this time, we have extended our collaboration to other groups, for instance, in ETH Zurich, or in the University of Lausanne, or in Cambridge Quantum Computing, with the idea of trying to assess whether quantum computing can be of help for processing data that comes from collisions of particles in these accelerators that they have in Geneva at CERN. Because the needs for computational power that they have at this laboratory is just incredible. It's estimated that in 1 second, when the accelerators are working at full power, more than 1 petabyte of data is generated per second. And of course, this is something that is very, very difficult to process or to store, or to try to extract as much information as possible from this experiment. So about 4 or 5 years ago, people at CERN, especially people at CERN Open Lab, were starting to wonder whether quantum computing was something that could be of help in processing this kind of huge amount of data. And then all these projects that they had started working on, some of them in collaboration with my group here at the University of Oviedo, crystallized in what is called the Quantum Technology Initiative at CERN. This was created a couple of years ago with the idea of making formal this exploration of the possibilities of quantum computing in high energy physics. And there are several like formal or government offices in this quantum technology initiative. For instance, there is this advisory board with representation from all the state members. And I have the pleasure and honor of being the representative from Spain. And I have been trying to help in realizing the potential of quantum computing for these tasks. In particular, this Quantum Technology Initiative at CERN is focused on 4 different ways of applying quantum technologies for real-life applications. Of course, they are interested in quantum computing, but also quantum sensing, also in quantum communications, and also in quantum theory. My work has been primarily on quantum computing, and especially on the applications of quantum machine learning, but there are many different projects going on in all these different aspects of quantum technologies. So I would like to at least give you a brief description of the problems or the projects I've been working on together with people at CERN under the umbrella of this Quantum Technology Initiative, especially in machine learning. And as you know, machine learning has many different flavors. You can talk about supervised learning, unsupervised learning, reinforcement learning. So I wanted to select one type of problem from each of these different branches and give you just a quick idea of what we are doing and what we are trying to obtain and to achieve with the application of quantum techniques. The first problem is a supervised machine learning problem, in fact, a classification problem in which we have events in which gluons, these fundamental particles, collide, and in the process, a Higgs boson can be produced. It is not always produced, but sometimes it is produced. And of course, it is interesting to know when the Higgs boson has been produced, to select those events and try to study properties of this particle. So what it's done is we capture some information about these events through 67 different physical variables that have to do with, well, I'm not a physicist, so I'm a little bit blurry here. I don't know all the details, but they have to do with what is the momentum of the resulting particles that come from this collision, what are the angles in the deflection of these particles. So we have these physical variables, and what people at CERN and at other different physics laboratories all over the world used to do was to apply classical machine learning. Okay, what we tried to do was to apply also quantum machine learning in the form of quantum support vector machines, on also quantum neural networks or variational quantum classifiers. We have tried many different architectures, many different ways of processing the data. The best results that we have obtained were through the use of what we call hybrid variational quantum classifiers, in which we have a first part of the classifier that is a classical neural network that somehow reduces the dimensionality of the data, and then a variational circuit that does the classification. And with this, we have been able to obtain classification performance that is comparable to what you get with big neural networks, but with much less parameters and with less amount of training data. We have published our results in this paper that is available at the archive, and we are now trying to extend our results and also to see what is the influence of noise, a problem that we have in current quantum hardware, and how we can somehow mitigate that problem in order to obtain useful results. Another problem in which we are working on is the reproduction of images that come from experiments, also from experiments in particle collisions, especially in calorimeters, in these detectors that they have at the accelerators. So this was something that had already been tackled before I joined the project by people from EPFL and from CERN Open Lab. And the idea was to use generative adversarial networks, but in their quantum version. And previously to my joining the project, they were able to reproduce the average image of this calorimeter energy deposit.
Awesome. So we do have a couple questions, Elias. So basically,
yeah, sure.
Kind of like building on regular machine learning. Now, Lorraine asks, can this classification also be carried out using quantum support vector machines?
Yes, we did, yes. And I did not show here the results, but in the paper we have some results, some comparisons to both variational quantum classifiers and to regular classical machine learning techniques.
Yeah, and then some more. So do knowledge graphs models used in quantum computing give more precise results?
I don't know. I have not used this particular technique. I know that there are some proposals of using quantum graph, quantum graph neural networks, but I'm not completely familiar with the technique.
Okay, and then Lorraine asks, building a quantum kernel in quantum machine learning classification seems to take a long time. So how can one mitigate that?
I'm not sure what you mean by that it takes a lot of time. Do you mean running it on quantum hardware, or?
Yeah, she says yes.
Okay, Well, I'm not sure that it takes a lot to run on quantum hardware, at least, well, maybe it's a problem with current quantum hardware. Maybe when we get better hardware, this won't be an issue, because I mean, the complexity is exactly the same as in the classical case. And here what we are trying to do is to find some advantage by working in a higher dimensional space, but shouldn't be slower, at least asymptotically slower than the classical case.
Okay. And then as you continue, if you could kind of highlight as far as like what's been done classically with machine learning and what's been doing, you know, with quantum to build on top of that.
In this kind of problem?
Yeah. Like I go to many places and they say, you know, some things in quantum actually build on classical, like we're not starting from scratch, like that kind of stuff.
Yeah, well, of course. I mean, all these techniques are somehow inspired in classical techniques.
Okay.
So for instance, with variational quantum circuits, what we try to do is to replace the kind of model that we learn with a variational circuit. But the whole idea is exactly the same as in regular neural networks, in which you have some free parameters that you optimize for with gradient descent or whatever, and then you have a good classifier because you are trying to minimize some loss function. So the idea with variational quantum circuits is exactly the same. Or the idea, for instance, with quantum GAMs, it's also to have this discriminator and this generator, and one of them is quantum. But the architecture is borrowed completely from the classical case.
Okay,
so
I think that's good news for a lot of us, because it's like, you know, the less, you know, investors want to hear, it's just like it's a brand new thing, these types of things. And you've already highlighted on the hybrid aspects. We haven't talked about quantum accelerators, but, you know, a lot of these, you know, cases are both classical and quantum.
Yes, sure.
Awesome. Okay.
No, I mean, I think we all agree that in the long term, I don't know, but in the short and medium term, we will have quantum computers coexisting with classical computers, and each of them will focus on those tasks that are better for the particular kind of computing. I mean, it makes no sense to replace everything with quantum.
Yeah, exactly. So any other questions for Elias right now? And you can unmute, and then if not, you can continue.
Oh, thanks. Okay, so well, we introduced this new architecture for quantum generative adversarial networks, which we call the dual PQC. And the novelty here is that we have two variational circuits, one that kind of selects the type of image that you want to generate, and the other one that's the generation. We have trained these systems, but they are quite difficult to train. They sometimes show problems with stability and all that. So we had to reduce everything a little bit, and we have published our results here. And recently we have always published a new paper in which we highlight the influence of noise when executing this kind of model in quantum hardware. And finally, I wanted to talk about a problem in reinforcement learning. Again, it's a simple problem, but I will tell you a little bit about more difficult problems in a minute, in which we have this this beam of particles that we need to steer so it goes directly to the detector. Okay, so this is a problem, a real problem in accelerator control at laboratories like CERN. And they solve this kind of problem with different techniques, like, for instance, rule-based systems, but also with classical reinforcement learning. And here we replaced the classical way of doing this learning of what is the best way of steering the beam with the use of a Quantum Boltzmann machine. And this is something that had been proposed in the literature, and we applied this to this particular problem, and we obtained quite good results. In fact, we have done a new run just recently last week, and we obtained a reduction in the number of interactions that the system needs in order to learn how to solve the problem of about 10-fold, okay? And for this simple problem. But for a more difficult problem, we are also with much more complicated structure of the trajectory of the beam and more detectors and things like that. We have also been able to obtain some advantage, and we have applied this in the real case. I mean, this was used in the real control of the beam, which is something that, well, I think it's quite nice that you can use a quantum model in a real case. And we have presented this at several conferences. We are preparing a paper with all these new nice results. And well, this is more or less the kind of project I've been working on. I wanted also to mention that another aspect that I'm very interested about in quantum computing is education. So I'm working here at the university and I teach quantum computing to my students. And when I was working at CERN, I was there for 6 months in 2020. I had the opportunity of teaching an online introductory course on quantum computing that you can find online, the recordings of. And it was very, very satisfactory for me. It was very well received. And I think that, well, it's an opportunity to reach more people and to let them know that, well, just as in my case, 5 years ago, I didn't know a thing about quantum computing. It's not so difficult. And you can easily, well, maybe not so easily, but you can learn about quantum computing by applying these quantum techniques to real problems. And I think that is quite interesting and a nice way of getting into quantum computing. So that was all I wanted to tell you. Thank you very much for your attention.
Definitely appreciate it. Now, going back to CERN, you said 1 petabyte per second. Many people believe that you can't do big data with quantum. Could you help clarify that?
Well, I mean, there are several proposals for that. One of them that is being explored at CERN, particularly by people who are at the Quantum Technology Initiative under this aspect of quantum sensing, is that maybe we can extract more information from data if we don't measure the data. These collisions are inherently quantum. So maybe if we have quantum sensors and we can somehow feed these quantum states into quantum computers, that can lead us to some advantage. And in fact, I think it was last week or a couple of weeks ago, there was some paper published at Science, I think it was, in which some researchers suggest exactly this with some theoretical results. So this is one way of trying to do this, because of course we have this problem of, if we have big data, if we have a lot of data stored, for instance, in a classical hard drive, how do we manage to feed all this data to the quantum computer? This is a bottleneck, okay? So maybe, of course, there is this proposal of using quantum RAM, of loading data in superposition, but this seems to be difficult to implement in practice. But maybe this idea of quantum sensing is the way to go. I don't know.
So you're saying quantum sensing, yes, more data.
Yeah, because you don't lose information when you measure. I mean, when you have a quantum state, you have a lot of information. When you measure that, you only can access a tiny fraction of all the correlations between the amplitudes and all that you have in your quantum state.
Awesome. Okay. Now, how many quantum computing journals are there? I saw you put quantum information processing. I'm sure a lot of us are curious.
I mean, there are many new ones coming out now. I mean, there used to be like less than a couple dozen journals, but now there are new ones. For instance, there is this one called Quantum Machine Intelligence. There is Quantum, which is very nice because it's open access and the fees for publishing are like very, very small, nothing to do with other open access journals. There is PRX Quantum. There are many new ones which are kind of new and young, but they are very, very interesting.
Okay, and one of the things, it was kind of your earlier stuff. You said semi-fields there was a 40-year gap. Now I think, so I can't remember who, I think it was two talks ago. Actually, it was a different one. It was somebody doing government research, and they're pulling up these old journals, right? And, you know, trying to extract information that they could use today for quantum. So there's that. And then I think, so Barry had mentioned that, you know, she likes the Turing machines. Could you talk a little bit more about that? And then Barry, if you have any questions, go ahead.
About Turing machines and the relation to quantum, do you mean?
Yeah, relation to quantum.
Yeah, I'm just that was just the first comment. I'm just a Turing machines enthusiast. I also studied them in graduate school.
Okay.
Oh,
and
great,
do you have
great.
any other questions for the speaker?
Not at the moment.
Okay. Anybody else? Any other questions for our speaker right now? Again, this is a technical talk, but it's also, you know, we can break it down as far as like what that means to other things. So we did have, I think Lorraine had asked, let's see, QML is a bit of a new field. So in regards to classification, has using quantum proven to be better than classical?
I mean, you can answer this question in two different ways. I mean, theoretically, there have been some results that prove that at least for artificial data sets, quantum computing can offer some advantage. Of course, all these results are relative to the difficulty that we have to show that there is some separation between quantum and classical computing. We don't know for sure. I mean, mathematically, we can't prove that quantum computing is more powerful than classical computing because we cannot even prove that P is different from MP. But assuming that there is this separation, you can prove that for some artificially created data sets, quantum machine learning is more efficient than classical methods. But on the other hand, we don't know if it is the case for practical problems. I mean, is this kind of data set something that you will find in a real life problem? We don't know. That is the kind of situation that we want to explore with this kind of project.
Awesome. So Anna, go ahead.
Yes, can you hear me?
Yes.
Sure.
So I'm interested in computer-assisted algebra. And so I'm interested in your work with the classification of the semigroups and using the unitary transformations in the algorithm.
Yes.
And do you use any systems for computer-aided algebra to help you with the calculations?
When we started working on this classification of semi-fields, we were using some software of that type, for instance, Magma, but it was very, very slow. I mean, I had to rewrite all our algorithms from scratch. I first wrote the programs in C++, but it was still very slow. And then I had to rewrite everything in C. So we found that, for instance, some classifications that had been done prior to our results in like 3 or 4 days of computing time, we were able to complete in less than 3 minutes. So we found that this kind of system is useful for some simple cases, but when you try to do something at scale, it's impossible to work with that.